I'm the research director for the Good System Smart City focus areas. I also the research scientist and group manager for the Scalable Computing Intelligence Group at TAG. The Good System is a UT Grand Challenge project with a mission to developing human AI partnerships that can benefit society. Smart cities technology have great potential to contribute to this mission. To advance our knowledge and research around smart cities, and we have started this presentation series every Tuesday mornings. So for today, we are delighted to have to feature the work of Dr. Niyogi. Dr. Niyogi is a professor at the Department of Civil, Architectural, and Environmental Engineering in the Collaborators School of Engineering at UT. Depth research seeks to significantly contribute to our understanding of Earth as a system, particularly the urban and agricultural landscapes and the dynamics role of coupled land surface process on regional hydroclimate and environmental extremes. So the focus of this research is the creation of climate resilient cities, coastal areas, and agriculture and predictive modeling as a dynamic system. Wow, so that seems really complex. So Deb, I will turn out to you now.
Thank you, Vijay. Thank you to the Smart City Initiative organizers, Feng and others, for inviting me. I recognize it's the start of summer, so several people would have different priorities at this point. We ourselves have our retreat going on for the department, so I hope this presentation would be available later for viewing, and it is essentially a pretty informal discussion about what we are doing to sort of introduce our program and get a sense about how we are trying to put the whole context of smart cities within the framework of sustainability, development, or climate resiliency, and so forth. So to give an idea, some of my group activities which sort of align to where I will be going with this is that our main goal is that we try to use technology with science and work with extreme events, whether these are extreme heat events, air quality episodes, fires, hurricanes, droughts. So the idea is that when you have a hazard occurring, if you can have technology intervene at the right time with information or some sort of a mobility or some other factors, then that hazard we can avoid from it becoming a disaster. For example, we had this winter storm recently in Austin, and it's predicted it's a hazard. And so we can't do much about trying to change the manner in which the hazard would be occurring. But when we have information available, what can we do with regards to the follow-up steps? It does not become a disaster or the impacts are muted a little bit. That's essentially one of the main goals that we try to achieve in terms of integration of technology within the decision framework that goes our way. So the end goal is to create tools and develop some learning environments that can help our own science community to take new advances, but also translate that to cities, to municipalities, not just in our neighborhood, but globally, and sort of try and create this global village perspective that everyone wins by knowledge sharing and open city framework and so forth. The framework essentially is built on four things that we will do with regards to smart city and other ideas. Discovery. A lot of what we do with our work is based on analysis of existing data sets. So we work with data scientists, we work with people who work with GIS, satellite, and other information, and try to look for that data. Then we try to study our environmental models and try to see if we are able to replicate those patterns. And when those patterns are missed out, we try to then understand what could be the processes, what could be the ways by this pattern could emerge. An example could be you have a line of thunderstorms that is coming towards Austin. And if you see the data that is for the last 10 years, you might find that a certain part of Austin gets more rain than other parts of Austin. Now, this is something that becomes as a data-driven knowledge. Now, if you are running our weather model over the city and we try to see the pattern, we try to identify this bias, then we can see there is a part of the city where we are getting a consistent bias where the rainfall is low. Then we start asking the question, is this because we are not representing some aspect of, say, vehicular emissions or some of the heating from the city? Or is it because we are using a old land use data which needs to be updated such that you get better circulation and winds and other factors? So those could become the kind of things we start looking in terms of developing the processes. Then we try to go in terms of innovation, which is really trying to merge what we are trying to do here, bring in the knowledge from different disciplines into our community. And this is where we are going beyond the physics-based approaches to AI, ML kind of approaches, where we can try to bring knowledge that is developed somewhere else into a domain area that is centric to our perspective. The end goal, of course, is usability, but usability cannot happen without scalability, meaning we can develop something which is for a prototypical region of, say, south of Austin or over Austin, but for it to be really useful, it has to be applicable as a much more generalizable framework. And so we work a lot in terms of scalability, and I'll be showing some examples as to what we're trying to do with the scalability. How do you take information from very fine scale, few hundreds of meters, to large scale, few hundreds of kilometers? Or how do you take information that is available of tens of kilometers or 20 miles and so forth and bring it down to 20 meters? So this upscaling, downscaling, that is a major part of usability. That is something we try to work with in our group, and I'll talk a bit more. So within the smart city framework, there are essentially numerous definitions and motivations that people have talked about. I mean, there's a very nice review that just came out from Wong and others, where we are talking about the blockchain and smart city as components that can be tied together in terms of the services that can go through. From our perspective, if you look at it, there are two ways smart city frameworks are being studied and put into the whole environmental setup. One is what we call the organic order, in which the cities are building on what they have, and they're sort of like growing like a biological entity. And the second is a complex system approach, which is sort of like a complex multiplex system of systems approach, that you might have mobility, you might have air quality, you might have heat, you might have the building growth, and all of these are networks in their own. And we have to somehow find the interconnectivity, the feedback, we have to create adaptation, and we have to see what are some of the self-organizing features that emerge from there. But there are also some social aspects that emerge. I mean, when people start thinking about smart city, they also think of cities being cool cities, that, you know, there's something good happening there. And these are the kind of things which are very difficult to model in an engineering-based system, that how do you calculate the happiness of a city? Or how do you put coolness of a city? Or how do you develop the resilient character of a city? I mean, when people talk about New York after 9/11, or when people talk about some cities in Asia after a rain event, they're back into business the next day. So that is the resilient aspect. And how do you sort of put the social feature into models? That's some of the things that we try to bring in, but essentially it is either looking at city which is growing organically, or city which is put together like Lego blocks of multiplexes that are trying to create this smart sustainable framework going forward. Our own working definition for this framework is that these smart cities are complex systems, they are scalable, and they have to be usable. Meaning we are not looking as some smart city as something which is just a piece that is sitting there. It is constantly evolving. It is complex. There are many layers, and it's scalable because you're going to have decisions which are going to be at a small scale, and there are decisions which are going to be at a governance scale, which is much larger. And the things that are being introduced in terms of creating that city smarter are often things that are usable. I mean, people are putting in things, whether it is sensors or technology or decisions that are being impacted that through the introduction of such technology. So its usability. So our working definition is that smart city aids livability and decision making through integrated technology at different scales. And this technology is not just physical sensors. This is, of course, computational aspects, conceptual tools that start emerging from this kind of work. So when I say decision making, I don't mean, as I said, just decision making at a large city scale, but it is even like micro scale. What do I do? What do I choose? Which road do I take? Uh, what kind of clothes I wear? What kind of economic activities do I invest in? How ready are we in terms of economic incentives? How do you plan for equity? How do you plan for disaster readiness? So all sorts of things, when people are trying to create the solutions, you need to have some data and you need to have this if-then technological tools that are built into it. And that starts becoming our framework for going ahead. So I'm going to share with you some of the examples of some of the collaborators like Jungfeng and others that we have been working with in terms of some of the active projects and activities that are underway. Many of these are still in pipeline. And so these are collaborative opportunities for our community to start working together on this framework. The first is that project we are doing with the city of Austin on heat and air quality analysis. This is based on where we are doing measurements by putting sensors outside or taking data from mobile sensors that are put in the car. There you can see it in the picture. There's a sensor that is put on a car and you drive around. And then you can create a map out of that mobile data set by combination of in-situ data plus the mobile data. There's also a very interesting partnership that is growing with Microsoft Research under their Project Eclipse, where they will be giving us some sensors that will be put within the campus, as well as with the city of Austin. And Jungfeng and I, we are collaborating pretty actively on this part. We also do a lot of modeling, and this modeling is at an urban scale, which is, and I've given some examples here, where you can see actually the UT bell tower in the extreme left picture at the bottom of the screen, where you can see the bell tower and the region around, and we are simulating the thermal feedback associated with that information using this model, which a lot of people in the urban community use, called the UMET model or the NVMET kind of modeling tools. The next to it is what we call a weather research or an urban weather forecasting modeling system, where you can see the location of UT Austin, you see Round Rock, Del Valley, and so forth, and you can see the thermal bands or the temperature at the bottom and the winds, and simulating the winds at a morning time as to how these winds would be simulated through the day, like you would have a normal weather forecast. So this is something we work quite a bit with our models, both at a very high resolution urban models to regional scale in terms of simulation of urban weather. And we also look at satellite data quite a bit in terms of, and this is a example of 2019 versus 2020 temperatures. We were trying to see the effect of COVID air quality and how these air qualities are different and the temperatures are different. Again, this is here Round Rock, this is Austin here, and then the Southern Austin and so forth. So you can see that this is multi-scale data set where you're going at a very small scale to a regional scale to much larger scale that go forward. So one of the key aspects that we constantly deal with is, as I mentioned, this notion of data integration and scalability that we are trying to make in terms of our smart city framework for decision tools. Most of our data that we have is typically of the order for 10 kilometer, and we typically have 10 kilometer to 1 kilometer grids where this information becomes available for environmental studies. One of the challenges is the scalability, that we want to go down from 1 kilometer to say a finer scale at 100 meters. And an even more challenge is when we discovered this, when we were trying to do some work in support of the COVID kind of exposure in an environment, in city environment, is what we call the personal scale, which is like taking the information of 1 to 10 meter area around you. How do you understand what is the environment you are being exposed to? We are calling it the personal exposure tool, or PET. In this personal exposure tool, we are really trying to understand the environment around us. And so this is where we have this tremendous opportunity for AI/ML kind of approaches, because Physics-based approaches can't go down to such a fine scale from 100 kilometers to 10 meters, or they're too difficult in terms of the approximations that we do are extremely computationally expensive. And so we try to use, as I mentioned, information that is available from different techniques. I'm going to show you an example of that ongoing work right now. We have a visitor, Dr. Manmeet Singh, who is working with one such AI approach from a very well-known work that has been done for image processing, where you have essentially a high resolution image and you're trying to you're taking a low resolution image and try to create a high resolution output from that. And this is a well-known CNN kind of problem that is known to the community. This paper, I believe, has been cited around 4,000 times or so. So here's an example. You have this is what you mean by a high resolution output, and here's a low resolution output. But what does this mean when you have environmental data? So we are taking 10 kilometer hourly data that is available from a Japanese satellite JAXA, and we are creating a boxes over Austin for this domain. And then we are trying to see, now we have this 10 kilometer data, how can we use this CNN or ANN kind of approaches and then try to scale it down for a much higher resolution. So we are looking at this with regards to different deep learning techniques in trying to scale statistical ways of getting environmental data down to much higher resolution. And in fact, several from our collaborative team with Jung Feng and others, we are trying to create a review paper out of the different techniques that exist for creating such urban scale information that is available. Right now, we have seen that the current signal to noise ratio from different techniques are starting to come up, that we are starting to get good signal out of our analysis, and we are continuing this training into the framework going ahead. Very quickly, I want to change gears to say what can we essentially, what is the literature right now and what is the agenda that if you want to go from this one small technique to other, as I mentioned, one key aspect is scalability. And so there's a mature effort that we had been doing with India, where I had gone for a sabbatical, and there is a model of models framework that has been created for the country to create a environmental service, so to say, an urban environmental services on urban computing. And there's a recent paper that has been submitted and should be upcoming in Urban Climate as a review. And it's about urban computing, managing air quality, and the sustainability development goals from the smart city perspective. And so what the framework is in place that we are trying to look at is that, in a sense, urban computing, which we look at, urban sensing, where you might have put sensors somewhere, you're looking at all the data that's being available from different sectors, and you're trying to put all that information together in trying to improve the livability within the city. It has a lot of promise, but cities, when we are looking at some more basic issue from an environmental perspective, we are trying to look at it in the context of environmental decision making. How do we improve the air we breathe? How do we distribute sensors around the city? What kind of data becomes available? How do you put all this information together such that we have better living experience within the city and what we'll call a smart city? So looking at the wide range of literature, there's hundreds of papers that were reviewed as part of this study for over 2 years. And what we find is that typically in urban computing environment, the smart city framework, when people talk about from air quality or the urban climate perspective, it is divided into 4 main categories: monitoring, modeling, urban intelligence, and decision supports. And each of that sort of like go in range of things. It could be the Internet of Things kind of framework, or it could be crowdsourcing information, or it could be actually running an air quality model as a service. It could be data fusion. It could be cloud computing. It could be data route activity that you get from different sensors. And then trying to come up with a service where people are trying to see, okay, how do I make new policy, whether it is for creating a new tax or whether it is for identifying vulnerable population. So there's a wide range for which this kind of urban computing has been used within the framework of what we call air quality and environmental sustainability going forward. Um, from our own framework that we put together for this particular project that was deployed at a national scale is we had four main components. We had urban meteorology, we had air quality, we had hydrology for flooding, and we had very high resolution computational fluid dynamics or CFD kind of models, which are looking at flows that are around the buildings and so forth. So if you have a vehicle going, how would the plume change and so forth. And the stakeholders were partnerships that we had and discussions we had with health community, the wind energy, the solar power, the city municipalities, the engineers from the cities, the director general of meteorologies, the secretaries who are in charge of the whole weather network and so forth, and getting all that information and trying to see how can we start looking at different cities and just find a way we can create a new set of analysis or a new set of service by bringing meteorology, air quality, hydrology, computational models and multiple scales, all the data analytics as a common framework, and then show that looking at this together, we have a better way of making decisions, we have a better way of helping the city move forward in terms of what you ought to do and so forth. So this particular work is actually in a pretty mature stage as well. It has been deployed. There is a nice paper that should be coming out in the Bulletin of American Med Society sometime this year. But essentially, that analysis that we have goes with regards to the traditional modeling that people have, or the big data analysis that emerges, or the integration of GIS with data systems that can, decision support systems that can be used together. And then on the other end, you have this whole new set of data that is coming from crowdsourcing, social media data sets, Internet of Things, mobile data sets, wearable devices, which has really not been utilized within the main framework of air quality modeling or urban modeling. And so this integration is where the new set of applications and discovery is really going, looking forward. So just to give an example, how is the low-cost sensors being used in the urban computing and urban air quality kind of work? This is from people looking at putting sensors on street maps, street locations, the lamppost, something that we are working with Microsoft and the city of Austin to try to do, developing data assimilation techniques, developing machine learning algorithms, developing ways by which we can use the citizen data with an actual sensor data and try to come up with a map. They're using ways for improving the resolution of the output. The example I showed for a rainfall, but there could be another example that could be done with air quality and identifying exposure for citizens such that we can give them advice as to what to do in the, and so forth. Clearly, AI is the game changer in many fields, including our own. And we are seeing number of applications that are emerging in both in this cloud, in this smart city framework with regards to what is happening for the environmental livability within the city by looking at in the perceptions, the impressions, or actual data crunching, to identification of hotspots, to developing guidance about what you can do with regards to activities and so forth. So this is, alerts and heat maps and so forth. And some of these things we have actually deployed as a service for by partnering with the city scale emergency responders. And this is something we would be looking forward to try and do in Austin in coming years going forward. Here's just sort of one example about the user case landscape where you have this number of networks that are tying together. It sort of goes back to my earlier point that smart city is a complex multiplex with usability, where you have people, like if you look at it, the asthma triggers, you have health exposures, you have decision support systems, you have models, you have education, you have actual models for studying the transport of pollutants, and you have infrastructure coming in from cloud computing. You have ability to do things with virtual reality. you are improved monitoring, you're giving alerts and so forth. So this whole ecosystem is integrated and trying to convey a sense of smartness with what to go. So what is our next steps and integration going forward? It's essentially bringing the structured and unstructured data together. This is in terms of the text, the CCTV images, the tweets, that we are all trying to have information and putting it into data. So this is sort of like the inverse problem. There's a lot of information. How do we bring it as a data that can be assimilated into our traditional models? Data acquisition. How do you deploy low-cost sensors? How do you put it on your cell phones, wearable devices, drones? How do you bring that data in? Data collection and processing. You have social computing and crowdsourcing. How do you know the quality of data? How do you start bringing it together? How do you talk about the heterogeneity in the data density? And then creation of what we have shown here, for instance, this cross-sector modeling framework, where you have weather as an input to air quality, as an input to urban scales models, as an input to health assessment. And this feedback, and then looking at health assessment from the other way by looking at crowdsourcing, satellite data set, low-cost sensors, wearable devices, sentiment analysis. So bridging these two worlds into one common platform, that's essentially where we are looking at machine learning and AI for value-added services. And then, of course, a big part of what we want to also do is this whole notion of augmented reality, so that we give this interactivity in the framework. I'll very quickly try to wrap up, seeing that I've already taken 28 minutes, is that the opportunities really are in the fit for purpose kind of approaches. That the integration, as I mentioned, trying to create these intelligence systems and data sciences. So there are really two types of problems that we have. One in which we have data, but we don't have the input to models. And in second case, we just don't have the data. And so we have to create synthetic data sets. And this could be something that you could have a satellite data and it tells you where is a city, but you don't know what is the kind of the width of the city or the roads or so forth, or the height of the buildings in a very efficient way. So we have to create that data. And so we have been looking at, say, I'm just giving an example of what it is in terms of creation of the augmented reality or the synthetic data that we try to use in our real world simulations of city, where we create such synthetic data about buildings and so forth. And then once you have this information available, you try to create this if-then scenarios. What would happen? Where should you do more greening in the city? Where should you do planting in the city? Where should you have heat mitigation technologies implemented? And this is the kind of thing that we try to do. So my collaborator, he created this digital network view of the city of Chicago. It is almost like you're flying over Chicago, but this is all being generated by computer graphics. And so you try to see, and you try, this is the city of Toulouse, for instance, and you do the same way. You try to get the information available from such graphics into a usable format. Then you start querying the information, look at the width of the city, the width, the height of the buildings, what kind of information is required over the models, what kind of trees might be growing, and greenness and so forth. And then try to use this to try and create and simulate cities where we can have a better heating prediction, where we can see how the winds are flowing in, where rains can form, where can we give flooding forecast and so forth, and going forward. So the excitement really that we have, as I said, is in terms of the whole notion of trying to get a sense of integration, multi-scale, multi-parameters, and multi-decisions. And when we try to put all this together by the right blend of embedded technology and techniques and newfound knowledge, we have a smart and livable city that is possible in a genuinely operational manner. And so that's essentially where we look for the opportunities to work and collaborate it and work it in the city framework going forward. So I'll stop at that, and thank you.
Thank you very much. It's very broad and informative talks, and you talked about a lot of the issues and what's what's application potentials. And I want to see if there's any questions for Dr. Niyogi. So I'm a more data person. So I'm actually quite interested in the data integration aspect on that. And I do feel there's definitely a need to do the data linking and to be able to combine different data together, not only just on the different scale, but more importantly on different dimensions as well. So we can combine air, water, energy data together. That can be something ultimately to do the simulation you showed at the end. So one of the things I'm wondering is, do you aware any of like existing platform allow people to do more like automated data linking or trying to scaling up that data linking process, or is it still mostly case by case manual process? Yeah.
Yes. So in some instances, like this project we had with a series of collaborators from India, this is being done as a service because it was part of a large high performance computing center similar to TAC. Um, then there are some projects where we are actually developing the World Urban Data Analysis and Portal tool, which is a community platform called WUDAPT, WEUDAPT. This is again a service that people can put in data and so forth. But for a large part, we are looking for partners like TAC and what you do, Vijay, and so forth, in terms of taking what we have and creating services, because that is where our scalability challenge lies. That we can generate the research platform, we can generate these ideas, then what next?
Mm-hmm.
That is where we really think there's a great opportunity possible.
Yes, I think I do feel that way. I think it is a very important question for the smart city. The data integration is a core for all the machine learning and AI algorithm, and it's also in smart cities the data is really very diverse and spread it out. So without a more systematic way to linking them, it's going to be really hard. Just you depend on people who has both knowledge on the domain science and on the data be able to make that conjectures. So yeah, so.
Absolutely. I agree with you. And I think one area I did not talk about is data authentication. I mean, when we are doing this downscaling and data integration, one of the big challenges that emerges is how do you know what you have generated is right? And that's where we have this very reliable dynamical models that we use on a daily basis for weather forecast and so forth. And that we can verify. You can get a forecast and you can verify with actual observations. And when we are saying we have developed a new technique, we can ingest that and compare it against the dynamical models and use the dynamical models as the observations or reality. And so that's another thing that we bring to the table when we are working with the AIML kind of groups about scalability and technique evaluation. And that will be another thing that we can try and deploy.
All right, so it's already 10:30, so I don't want to drag everybody here too long. So if there's no more question, I really want to thank Dr. Niyogi again for this wonderful talk. We are record the meeting, so we will posting the recording of the presentations through our website, which is smartcity.tech.utx.edu. And we will have another talk next week. So that's going to be our final talk for this semesters. Thank you very much for
Thank you.
everybody's coming, and thank you, Dr. Naoki, for this wonderful talk. See you next time.
Bye.
Bye.